Hey guys, today we're learning comparing linear, exponential, and quadratic models. So we're going to compare linear, exponential, and quadratic functions. If you look here at our linear function, our equation is y equals mx plus b. That's our equation in slope-intercept form, right? M is our slope, b is our y-intercept, and we draw our line on a coordinate plane. That's all about linear. Looking at exponential, if you remember this, our equation is y equals a times b to the x power. It looks like a boomerang, right? And it's increasing exponentially. The x is our exponent. Cool. And our new one that we're really focusing on this chapter is quadratics. So I have y equals ax squared plus bx plus c. Even if you can't see this well, that is your equation, that standard form equation. And when we have our graph, our parabola is the graph on the coordinate plane. Okay, cool. So this is all stuff we know, just reminding you of us. Make sure you have this. Now, example 1. Plot the points. Tell whether the points represent a linear, an exponential, or a quadratic function. So we have 5 points here: 4, 4, 2, 0, 0, 0, 1, negative 0.5, and negative 2, 4. So get all this down. Okay, ignoring all of this stuff, right? So these are our 5 points that you just plotted on a coordinate plane. And we're looking at this shape. What does it look like? Does it look like that line? Does it look like a boomerang? Does it look like the parabola? And if you're looking at it, it should look quadratic. So when we plotted those points, you got a quadratic function. Now I want you to try B. B here is 0, 1, 2, 4, 4, 7, negative 2, negative 2, and negative 4, negative 5. When you finish B, you can unpause the video and listen. So when we plot these 5 points, 0, 1, 2, 4, sorry if you can't hear me, 4, 7, negative 2, negative 2, negative 4, negative 5. What does that look like? What type of function? Linear, exponential, or quadratic? And it looks like a line. So this is linear. Okay, and lastly we have here 0, 2, 2, 8, 1, 4, negative 1, 1, negative 2, 0.5. Plot these 5 points on their coordinate plane and see what you get. Unpause when you get there. So I have the point 0, 2, 2, 8, 1, 4, negative 1, 1, negative 2, half. So that's really messy looking, but hopefully it looks better on yours. What does it look like if I were to connect those blue? And I can see it looks like that boomerang. So this is exponential. So this is something that I expect us to know at this point. Exponential. Cool. So now we need to know more than just can I plot these and get what kind of function they are. So let's talk about the differences in ratios in functions. So let's look here. We've got a linear function, y equals 2x plus 5. Get that down. Then we have a table that corresponds to this linear function. So my x value is negative 2, negative 1, 0, 1, 2. And the corresponding y values is 1, 3, 5, 7, 9. Okay, so we want to see what's happening here. So we start with our x values. What's happening from negative 2 to negative 1 to 0 to 1 to 2. And every time it's plus 1, plus 1, plus 1. All right, cool. And then let's look what's happening to our y, right? From 1 to 3, plus 2. From 3 to 5, hey, plus 2. From 5 to 7, plus 2. From 7 to 9, plus 2. So let's look at our equation. I'm going to rewrite it. Y equals 2x plus 5. Well, where's that coming from? Our slope is our change in y over our change in x. plus 2 over plus 1 is 2. And it's the same every time, plus 2 over plus 1. Change in y over change in x. So this is that part. Where's that 5 coming from? Well, look at what you got here. 5 is our y-intercept. So that's this point here, 0, 5. So that's why that is coming from. All right, cool. That's pretty messy. Hopefully you paid attention as we went along. Now let's look at our exponential function in green here. We have the equation y equals 4 times 2 to the x power. And we have our table says -2, -1, 0, 1, 2, same input for x. And the corresponding output is 1, 2, 4, 8, 16. Get that down. Then start looking at what's happening. So from -2 to -1, from -1 to 0, from 0 to 1, and from 1 to 2, every time it's +1, +1, +1. So you can kind of ignore it when it's a +1 in all cases. Now let's look at the denominator. I've got a 1 to a 2, so that seems like a +1. 2 to 4, is that +1? Uh-oh, doesn't work. So that means it's not a difference. Here, +2 is a difference. Here, it's a ratio from 1 to 2, 2 to 4, 4 to 8, 8 to 16. It's being multiplied by 2. And that's this part of our equation. And the other part of the equation is 0, 4. 4 is our y-intercept. So if you remember, y equals a times b to the x power. A is our y-intercept. That's really tiny. And b is that common ratio. Common ratio. In other words, what's being multiplied here, our slope is our common difference. All right, let's take a look at our quadratic function. This is the hardest of the three, but we can do this, no big deal. Quadratic function, the equation we're using is y equals x squared plus 2x minus 1. Here's the table that represents this function. -2, -1, 0, 1, 2 is my input for x. My corresponding output is -1, -2, -1, 2, 7. So this should look automatically, you should see, all right, this is weird. It's not that U-like fashion. It's not the same here and here. And that's because we have a b value. And we used our standard input. But that's not the point here. That's not what we're looking at. Let's start looking at our x values from -2 to -1, from -1 to 0, from 0 to 1, and 1 to 2. It's adding 1. But that doesn't matter. So we're looking now at our down here, right? I'm going to erase what I even had. From -1 to -2, what's happening? +1. Sorry, that's not true. -1. From -2 to -1, that's +1. From -1 to 2, that's +3. From 2 to 7, it's +5. So now, with quadratics, you are not going to see the same thing happening. Even multiplication, that's not going to work. -1 times 2 gives me -2. -2 times 2 is -4, not -1. So let's do, for quadratics, you actually have to do 2 rounds. So from -1 to 1, that's our second round. -1 to 1 is +2. 1 to 3, +2. 3 to 5, +2. So when it's a 2-rounder, it's quadratic. You can also look at it based on that you do have a u. Sometimes you'll see the u with your range. All right, cool. So this is a double common difference for quadratics. Now, lastly, almost done, guys. Practice a little bit. Tell whether the table of values represents a linear, exponential, or quadratic function, and then if you can, write the equation that represents this function. So go ahead, pause the video, and try these two. Good. Now play that video. Let's look. We've got +1 in the top, so I'm going to ignore it. down here, I've got from 11 to 8, 8 to 5, 5 to 2, 2 to -1. Every time it's -3. So if it's minus, that is linear. Cool. And if you feel like you can write an equation, that's awesome. Y equals mx plus b is our slope-intercept form equation. What's my slope? Well, whatever is happening is my slope. Y equals -3x. What's my b? That's my y-intercept. Do I have that point? Yeah, it's right here. When x is 0, y is 2. So I have the equation y equals -3x plus 2. Okay, let's work over here. Looking at my x values, plus 1, plus 1, plus 1. Check, done. Here, 0 to -1, -1 to 2, 2 to 9, 9 to 20. We got a -1. We've got +3. We've got +7 and +11. No pattern, clear pattern. Let's try it again. -1 to 3. What's happening from -1 to 3? That's actually +4. 3 to 7, +4. 7 to 11, +4. Now, writing equation for a quadratic. Y equals ax squared plus bx plus c is not as easy as a linear or even an exponential. Both of those are almost no big deal. For this, you really need to find your, plot it, find your axis symmetry and kind of work your way backwards. So, and see if that, so for this one, we're not going to write an equation just yet. For anybody who gets there, we get to that advanced level, that would be good. But for now, let's just stick with writing equations for linear and exponential. Okay.